Okay, so for the next section, we're going to have a look at indicators, the ranges of indicators, the different types of indicators and how they work, and then also some titration curves, so we'll have a look at those. So the first thing we've got to look at is some acid-base indicators, and we'll have a look at the three main indicators that we use. So the first one that we would use is methyl orange. And we're going to be summarizing these and how they work. So methyl orange generally has a range of between 3 to 5. Now, what that means for methyl orange is it has two distinct colors that we can pick up from our eyes, from human eyes. So at the lower end of the range, at around 3, methyl orange has a red color. And it changes into a yellow color when it gets above 5. So this is the 3 and this is the 5. What is it between 3 and 5? So if it's somewhere around 4, the pH is somewhere around 4, you would have a color that's in between red and yellow. But at a pH of 3, it is distinctly red, and at a pH of 5, it's distinctly yellow. Anything in between then gives you a mix of the colors. The other one then that we have is, well, we'll move up the chart, is litmus is the next one. So litmus detects things in between 5 and 8, a pH of 5 and a pH of 8. And again, the same thing with litmus. Litmus is distinctly red and an acid. So anything below 5, so less than 5. And anything that's greater than 8 in litmus is going to be blue. And we've seen that with litmus paper. The same thing occurs with litmus liquid. And then finally, the last indicator that we have is phenolphthalein. And phenolphthalein then works between 8 and 10. So when it's less than 8, phenolphthalein has no color at all, it's colorless. But when it's greater than 10, phenolphthalein turns pink. And this is something that you need to know. This is something that you're going to have to learn off because you'll be asked questions about it. So let's look at the next part. Sometimes you may be asked, how do indicators work? So let's have a look at an example using litmus. So the first thing to note is indicators are generally acids. But they're weak acids. And when we use them in a titration, it doesn't really matter. It's not going to throw off the titration because we only use 1 or 2 drops of the indicator. So it doesn't affect the overall experiment. But again, the fact that they are weak acids, they are proton donors. So the molecular structure and the formula for indicators like methyl orange and phenolphthalein and litmus are actually quite complicated. So what we do is we tend to shorten them down. And what we'll do is we will write down HIN to represent the molecular formula of an indicator. And again, the reason why we have it as HIN, the IN indicates that it is an indicator. And the reason why we have a H is because it's a weak acid. So this is going to be a proton donor. So this here is the formula for your indicator. So what we see when we're using this is we find our indicator goes through an equilibrium reaction. So you have H plus IN minus. And the reason why it dissociates down is the protons become free in solution. This here, if we're looking at litmus, which is the one we're going to be checking out, your indicator is going to be red. That's for an acid. And this one will be blue for a base. Now let's examine this and see how it works. So imagine, if you will, you have a beaker, and inside in the beaker you have put in an acid, and inside in this acid is HCl. Now what does it mean to have an acid? Well, basically inside in here you have lots of H pluses. So you have a H plus here, you have a H plus here, you have a H plus here, because acids are proton donors. There's lots of H pluses. So if you put in an indicator into your acid, what are you doing? You're adding an indicator. Therefore, you're adding more H pluses. Now, at the moment, this is fine, it's balanced. But what happens is when you add more H pluses, there is too much H pluses. And because this equation here is an equilibrium reaction, we have to think back to chemical equilibrium. The system will do its best to relieve any stress that's applied to it. When you add more H pluses, this is a stress applied. You're increasing the amount of H pluses. So what does the system do? The system will go in the opposite direction to swallow up those H pluses. So in this particular equation, it goes in this direction. Why? Because going from right to left uses up the H pluses to form HIN. Remember, moving from right to left forms HIN. It uses up these H pluses. So the equation, if you add in more H pluses, is going to produce more HINs, and that turns it a red color. Now that's what we see in the lab when we take an acid and we add an indicator like litmus in an acid, it turns red. The same thing applies then for when you're adding it to a base. So again, same thing with a base. What have we got in the base? Well, our base is OH minus ions. What happens when we add an indicator? We are adding H pluses. So when you add the H pluses, you are going to increase the concentration of H pluses. In other words, the equation is going to move in this direction because you're increasing the amount of H pluses. And by increasing the amount of H pluses, you are also increasing the amount of ion minuses. And the ion minuses is a blue color. So that explains why when you put a litmus indicator into an acid or a base, it gives you a red or blue color. Again, all of this is on the Leaving Cert course and is important for you to know.